Okay, we'll just wait a minute or so until we get some more people coming in.
Good.
Okay, so welcome to everybody who's just signing in just now, and it's the latest in our NMIS Insights online webinar series. And today we're focusing on future-proofing manufacturing with Industry 4.0. So I'm going to pass you over to Sam Hume, my colleague, who will start the presentation. Thank you.
Thank you very much, Laura, and good morning, ladies and gentlemen. Welcome to the National Manufacturing Institute Scotland NMIS Insights online webinar titled Future-Proofing Manufacturing with Industry 4.0, recorded today on Wednesday, the 4th of November, 2020. Introducing the speakers this morning, we have Mr. Richard Miller, Mr. John Riley, Mr. Thomas McMaster, and Mr. Jafar Junaija, who are all members of the NMIS digital team. And my name is Sam Hume, and I am the Partnership Development Leader for the digital team here at NMIS. A few housekeeping rules before we begin, ladies and gentlemen. This webinar is being recorded and will be made available on our YouTube channel. Your microphones and webcams will be turned off during the session to avoid background noise. You can type your questions throughout the session via the chat tool, and please do. Time will be allocated at the end for the speakers to answer your questions. Use the hashtag NMISinsights for any questions on Twitter at NMIS_group. And please take some time to complete our survey that will be sent out after the webinar. What is the National Manufacturing Institute Scotland? The National Manufacturing Institute Scotland is a group of industry-led manufacturing, research and development facilities where research, industry and the public sector work together to transform skills, productivity and innovation to attract investment and to make Scotland a global leader in advanced manufacturing. NMIS will increase productivity by reducing barriers to innovation, stimulate investment and increase manufacturing competitiveness, catalyze job creation and strengthen supply chain links, inspire and attract talent and equip current and future workforces with the skills they and businesses need, and work with manufacturing businesses of all sizes in multiple sectors, providing benefits across the whole of Scotland. NMIS is part of a One Scotland team operated by the University of Strathclyde, Glasgow, supported by the Scottish Government, Scottish Enterprise, Highlands and Islands Enterprise, the High Value Manufacturing Catapult, Skills Development Scotland, Renfrewshire Council, and the Scottish Funding Council. The following infographic depicts the structure of the NMIS group and its core elements. The sections in yellow are open now, in purple are in development, and in pistachio and teal are opening in 2022. Thus, the key message here is that although the building is not due to open until 2022, NMIS is here and open for business. NMIS is made up of the Specialist Technology Centres in yellow, the Advanced Forming Research Centre and Lightweight Manufacturing Centre, as you will know, are already well established. We are not waiting for the Manufacturing Skills Academy, Digital Factory and Collaboration Hub to physically open. Work has already begun and we are open for business. The Manufacturing Skills Academy has already continuous professional development courses in place, whilst work is already being done for the Digital Factory by the AFRC's digital team. In summary, the new NMIS building has been approved, and although not now open, work has begun and support is available to you. And with that, it gives me great pleasure to introduce our first speaker this morning, Mr. Richard Miller. Thank you, Richard.
Thank you, Sam. Good morning, everybody. Thanks for joining us this morning. I think I wanted just to start off with giving a sort of not an exhaustive list of the common challenges facing manufacturing today, but certainly some of the main elements that organisations are facing at this point in time. With regards to costs, running the day-to-day operations of a facility is expensive, especially when you're looking at the maintenance of machinery and processes, and obviously looking after staff and salaries, etc. But the other challenge is the level of investment required for implementing digital technologies through, or even looking at acquisition of mature digital technologies and any additional development costs to support that. Some of the other challenges could be applicability, looking at the plant, the process of the product, and maybe thinking it is too complex or not suitable to Industry 4 transformation. Staff, so not only do we have the challenge of upskilling staff with new skills to support the deployment of these solutions, but we're also aware that there's a skills shortage across Scotland, where there's been a shortfall of people working in the manufacturing sector over the last 5 or 6 years, from about 189,000 to 182,000. Obviously, other challenges are globalization, so competing in global markets, which means we have shorter product cycles, reduced time to market, reduced development cycles, and more customized products. So that means that organizations are having to work more agile and much faster time constraints. Obviously, as everybody's aware, COVID-19, the reduced demand on manufacturing for standard products is reducing due to the reduction in public consumption of products and services. And then companies are looking to pivot to maintain their business through other requirements, such as the manufacture of PPE. Brexit, well, we all know what Brexit is, and obviously the potential for increased costs and bureaucracy in the near future due to the current status of the free trade agreement negotiations. And finally, one of the main elements is climate change and reducing carbon footprint and output through net zero challenges and developing eco-friendly products and services. Obviously, Scotland's target for net zero emissions of greenhouse gases is to be net zero by 2045. So obviously, manufacturing has a large role to play in that challenge as well. Sam, can you go into the next slide, please? So what is Industry 4? Well, it's the fusion of physical, virtual and digital worlds to help develop the next industrial revolution. It is to manage and maintain a system through a network of connected devices that is able to continuously operate by adapting to internal and external influences with minimal human intervention. And this paradigm is founded upon the 9 pillars, which we'll go into next. Next slide, please, Sam. So 9 pillars was really founded upon in Germany around about 2011, and it looks at autonomous robots, simulation and modeling, system integration, Internet of Things, cybersecurity, cloud computing, additive manufacturing, augmented reality, and big data. And we can look at these 9 pillars as a framework to create a structure to digitize manufacturing through the following. So we look at data acquisition from process. So the Internet of Things, the advent of the World Wide Web and the widespread development of low-cost sensors coming together to create a data-rich environment. Systems integration. So integrated systems allows connection of planning systems to support production and manufacturing facilities through more readily available open source software solutions to enable that better connection between shop floor and the office. Data storage. Development of technology allows more data to be stored more readily. The challenge here for organizations is to understand how to develop a secure solution that is appropriate for their manufacturing organization and their business needs. Visualization is really the visualization of available data that enables companies to assess and understand manufacturing data much closer to real time than previous methods. This enables a more agile capability to organizations. Again, that level of visualization is really dependent on the requirements of the end user. So it doesn't need to be a fully 3D virtual world scenario. It could be simple as a 2D dashboard that gives them some graphs and charts and allows you to see the data as soon as it's created from the process. If you go into the next slide, please, Sam. So what I want to try and do, looking at the 9 pillars, looking at trying to understand that challenge around fusing digital, virtual and physical worlds, is to try and create a framework for manufacturing. And really the first 2 pillars, 2.5 pillars from the left-hand side working through is things that is elements that companies already do today effectively. So when we talk about digital masters, we're talking about computer-aided design, computer-aided manufacturing and engineering. So around modeling and simulation, and model-based definition is something that's coming new. But I mean, those first 3 really are, standard, services that engineering companies and manufacturers already work in. This technology has been developing for the last 20, 30 years. And it's the same with control systems. These have been developing since the late 80s and early 90s around the increase in computing power for maintaining and running machining centers, etc. And also, within the white box, within these digital masters, we look at product lifecycle management, product design management, and ERP, so your enterprise resource planning. These are all elements that work together within the office space, maintaining the revision control and understanding and the operation of a manufacturing facility when it's producing something. Now, what we can do within that first pillar is we can start to create some digital solutions in there around standard operating procedures and work instructions, and allowing that information to be deployed readily and remotely to workers on the shop floor. That gives them much more instantaneous access to information and understanding of what the process is trying to do. So we're reducing that amount of communication between the office space and the shop floor, and it's there, it's readily available, and it's updated in real time when there's any mods or updates to any of the design information within the management systems. Then we go into the next stage, which is around about physical masters and the fabrication, the assembly and installation and commissioning of whether it's systems or manufacturing plants, etc. And these elements all have certain items that we can start to pull data from. So we look at the programming logic control of machining centers or manufacturing or automation centers or manufacturing systems. We have that lower level within the SCADA framework as well, where we can pull data, raw data from the machines to start understanding what the performance of that's doing. On top of that, and like I've already mentioned, is the development of low-cost sensors that can be deployed through a wireless network or even a wired network, depending on what the application is, can add more data to your processing and understand more information of what's happening in your process. And these sensors and the PLCs and the SCADAs can all be connected through different network configurations that allows you to have a protected solution on the shop floor, but it also has that control of not interfering within your IP areas in your office environment. And again, we can build around the digital elements, the standard operating procedures, the work instructions for these elements, and deploying those through augmented or virtual reality solutions for training or for access to information on the shop floor when required. You can also have screens on your shop floor that can visualize this information because all the data is there based on your web network. Then obviously we go into execution. So we're talking about training and operation of staff, training of staff and operators of equipment through the training process. Again, looking at your standard operating procedures in a digital context, your work instructions, etc. And we can also understand from the execution process, the key process indicators and key process variables of what your manufacturing process does. So if you do a little bit of upfront work around value stream mapping and information and systems management, you can understand what those are, so you can identify what level of data acquisition that you want to have, and then able to transfer that information through your connected systems back into your shop floor and back into your office environment to understand the managerial requirements to support the execution of your process. And then we've got storage, which is something that's developing more rapidly as we come along through this industrial revolution. So we're looking at IoT platforms, whether that's open sourced or whether that's, you know, privately owned, these are available where you can visualize your data much quickly. You know, you're looking at visual block programming to easily develop and understand and visualize what your data looks like. Cybersecurity is a more challenging element within the storage requirement, and a lot of companies provide inbuilt cybersecurity options and align with your ISO accreditations and the HSCOG 86 accreditations. So there is solutions out there that can be readily deployed. There are other organizations that are developing solutions as well to support on top of what you might already have, or look at alternative options. And obviously feedback is where, you know, it really looks at that, you know, that automated control of your process with little human interaction, and it's all about, you know, taking the visualization of the information, applying analytics and you know, algorithms and machine learning algorithms to your data to understand the trend that's going on in the process, and then be able to react as quickly as possible to any changes that are unfavorable to your operational conditions. And again, you know, some of these systems already exist, whether it's a manufacturing execution system or whether it's a condition monitoring maintenance system. These systems do exist, and it's about how do you look at upgrading or developing that further. And again, we can look at, with the digital element, as the AR and VR solutions for your data visualization. And again, that could be a simple 2D dashboard as well. So again, it all depends on what that organization is looking for, and trying to, you know, become a much more data-rich process to manage your process much quicker. Okay, Sam, we just go on to the next slide, please. So having spoken about that briefly, I wanted to give a quick overview of a project we recently completed with Diageo, Siemens and KigTech, where, you know, we were looking to, you know, improve cask production. That fill level is extremely important for distillers, especially when you hold over 11 million casks in maturation. So the average standard was roughly about 94%. You know, we wanted to improve that by 5%. Now that might not seem a lot, but, you know, if you look at a 200 litre cask with 94% fill, you know, that's about it's about 12 litres, I think you're short of. And then if you apply about 11 million casks, that's a lot of whiskey that needs to get filled, and additional logistics and barreling. So we wanted to try and tackle this problem by you know, removing overspill, underfill and foaming, and provide real-time data in the cask filling process. So you give us the next slide, Sam. So the key requirements: we wanted to accurate, repeatable fill, we wanted to minimise air pocket in the cask, no overfill, we wanted to eliminate any flexible hosing, we wanted it to be easy to use for the organisation, we wanted that fill time less than 60 seconds for 200 litres. It has to be ATEX approved, and the casks are obviously not uniform, so these are all handmade, and those have inherently small changes in the volume that you can have internally. So again, it's about having that automated control. And you can see on the right hand side is our effectively our digital model, our CAD model of the finished system. And again, this is something that we have done as a standard practice, engineering practice, using our computer-aided design. And we'll obviously go on to the next slide, just go in a bit more detail. Just press it again, Sam. And again. So again, I wanted to refer back to the previous slide and looking at, you know, the sort of digital masters, the physical masters, and looking at the execution. What we wanted to show here was, in its simplest form, you know, at the bottom level, we have our plant machine and our simulation of that plant behavior. So that would effectively be our digital master. And then as we develop the physical BOM for the actuators and the sensors and the I/O devices within the control panel, we can develop that virtually as well with a virtual PLC solution. So we're looking at software in the loop and looking at the simulation of the signals from these I/O devices and sensors, and controlling the operation of the system. You could go down the hardware in the loop solution, but that obviously adds more capex to your project. So again, we went down the virtual route. And then as you get to the top two layers, the PCS7 system and the cloud data, those are actually real No, so that virtual PLC that we created, we just dropped that into the physical asset and started running the machine. Now that allowed us to reduce installation commission time of the system from about 5, 6, 7 days on this because of the size of the system to about 2 days. We had a fully operational system implemented within 2 days. And again, once we started doing that, we were able to store data in the cloud from our technology partners in the project. Okay, Sam, we're going to the next slide, please. So really, the results of the filling system, we were able to do a 5% improvement on those industry standards. You know, we repeatedly filled 99% of a 200-litre cask. We did several hundred tests on this. We reduced the cask fill cycle time by about 33%. And we had no underfilling or overfilling. So again, it was highly repeatable. It has the opportunity and impact to save the industry millions of pounds each year in logistics, warehousing and inventory costs, but it also provides the SME KigTech a new product and service offering into the industry as well. So there's a kind of a win-win situation for all parties, where we were able to showcase a new solution using these digital technologies. We were able to improve the process physically. We were able to provide a new offering to the organization. So it was a win-win for everybody. And if you go on to the next slide, please, Sam. So what were the benefits of what we did here around our digital twinning element was we planned a lot prior to committing to capital expenditure. You know, we applied the training that these control system engineers had into the deployment and development of the virtual PLC, and we were able to remotely connect workers to the HMI system using, you know, the latest Wi-Fi technology and remote handsets. We were also able to understand data much better with regards to AR headsets and visualizing information in real time against the instrument and process time. Again, we were able to understand the operation of the system as close to real time as possible. Obviously, there is a slight lag due to the transfer of data. You know, that allows us to be able to respond to those critical situations faster. And we were able to reduce the downtime as well. That leads to reducing downtime for machines as well. Obviously, you know, developing all these processes and these solutions gives us a much more competitive solution within this globalized food and drink sector. It gives a solution that's faster to market as well through the reduced development cycle time, and it offers a customized service to our other distilleries and breweries, etc. So there's lots of different benefits to what was achieved within the project, and I hope I've managed to showcase some of the solutions that digital technologies can provide to some of the manufacturing challenges in the short time that I've had, and now I'll pass over to my colleague. Okay, thank you.
Thanks, Richard. It was really quite interesting. So I'll be talking about Resume. So what is Resume? Resume, the acronym stands for Resource Efficient Supply and Manufacturing Environment, which will bring all NMIS facilities into the fourth industrial revolution. The aim of Resume is to create a suite of intelligent and connected systems in order to illustrate and test the possibilities for a streamlined supply chain network, demonstrating effective working of data-driven manufacturing and supply at machine, facility and enterprise level. Resume will comprise of hardware and software solutions aimed at integrating manufacturing equipment and supporting systems across all NMIS specialist facilities such as AFRC, LMC and Digital Factory. All of this under the ISA 95 model. The testbed will support and develop, sorry, Sam's doing the previous page, but the testbed will support the development of novel digital factory solutions aimed at our industrial partners and the wider Scottish and UK manufacturing communities, while still being able to scale for both SME and larger enterprises. Next slide now, please. Thank you. The Resume testbed is modelled after the ISA 95 structure, which is for developing an automated interface between enterprise and control systems, and the standard has been developed for all industries and processes. The structure sets out communication and interface protocols for automation in manufacturing environments. The model adopts a hierarchical architecture to separate layers of communications from sensor systems embedded within machinery through to enterprise resource planning software. As you can see, the foundation of the model is the sensors and signals, which retrieve data in the microseconds to millisecond range, connecting to the PLCs working with data in the tens of second range. Going further up the model, it connects with the supervisory control and data acquisition, then the manufacturing execution system, and finally the enterprise resource planning. Using this model, you can understand exactly how an automated system can be organised and built. Next slide, please, Sam. Using the ISO 95 model as a guide, the work package for Resume has been split up into industrial IoT, networking, data storage, data analytics, and enterprise integration. Industrial IoT will focus on enabling the connectivity between machines, sensors, other devices, and network layers. The challenges will be connecting all manufacturing equipment at NMIS facilities and communicating that data over a network to a storage solution. Networking will focus on developing the communications platform that will support data transfer between all systems within NMIS. Our aim is to install and operate a private 5G network for our data communication. The challenges will be integration with existing communication infrastructure and enabling wireless connectivity with similar capabilities as Ethernet cable, as we want to achieve use cases like real-time control, which require large bandwidth and low latency. Data storage will focus on creating a scalable on-premise storage solution that will have distributed storage nodes all across NMIS sites, allowing data to be stored from multiple machines and systems. As it will store different types of data, the storage solution will be a data lake, which stores data in its native format until it's needed. The challenges will be ensuring scalability, accessing all data at every NMIS site, and having fast access to that data. Data analytics will focus on creating a data analysis cluster on-premise that will support both real-time and historical data analysis, along with production analysis model deployment. The challenge will be creating a container-based software platform, enabling third-party solutions, and transitioning development models to production environments. Finally, the enterprise integration will focus on enabling operational oversight of the test bed and interoperability with existing ERP systems. The challenges are enabling dynamic scheduling of digital factory resources, ensuring outcomes of data analysis models are communicated effectively to supply chain, and developing responsive mechanisms to detect issues. Next slide, please, Sam. NMIS current manufacturing equipment and communication infrastructure is highly vendor diverse, with multiple industrial partners collaborating on different test beds and developing customized solutions for many applications. As such, interoperability is critical to the development of the Resume testbed. Overall, NMIS facilities have 142 machines, with more machines being added each month. Currently, 117 machines are controlled by a PLC or CNC and have HMI that can potentially communicate with external devices via protocols such as Modbus, Profinet, Ethernet, RS-232, RS-422, etc. This leaves us with 25 machines with no connectivity. These machines are cranes, welders, bandsaws, etc. We will install sensors onto these machines to retrieve meaningful data such as if it's on or off, power consumption, and total time used. Next slide, please, Sam. The lessons learned from Resume will help with the construction of the new NMIS digital factory, which we will be able to replicate for Scottish and UK businesses. It will also allow other test beds within NMIS to grow, such as Zero Capital Factory, Reconfigurable Factory, Remake, Autonomous Lab, and Future Forge. Zero Capital Factory will build on the Resume architecture by extending to a business model where no investment in capital is required for a business without manufacturing equipment. An environment where factories are established on a membership/subscription-based model. Reconfigurable factory will be a modular manufacturing environment. This will allow rapid configuration to support fast-paced manufacturing environments with rapidly changing customer requirements, enabling the supply chain to be more agile and responsive. Remake will be a manufacturing facility focused on testing and development of remanufacturing, repairing, reusing, and repurposing end-of-life components. Autonomous Lab will create a materials testing facility operated completely by autonomous, dexterous, and aware robots driven by deep reinforcement learning. Finally, FutureFolds is a state-of-the-art forging facility which will be fully digital enabled, taking simulation and data utilization towards grain structure prediction to understand life effects from open die forging. As you can see, the resume testbed will help digitize all these other testbeds within NMIS, creating efficiencies and new opportunities which were not thought possible. Again, thank you for listening, and I will now pass you over to Thomas, who will discuss the challenges and opportunities of integrating Industry 4.0 with automation. Thank you.
Good afternoon, indeed, everyone. As John said, my name is Thomas, and I work on automation projects within a digital team at NMIS. I'm going to talk today about autonomous robots within Industry 4, which, as Richard said, is one of the 9 pillars which were mentioned. Starting off with a very brief history, I'm going to outline how we as humans interact with robots when it comes to programming them. So first off, we started with online programming, either plugging in a teach pendant, as you can see in the picture, and giving instructions, or using the lead-through approach. So, literally taking the end effector and robot and taking it around the path it should follow. From that, we then moved to offline programming. So either using a GUI with a model of a robot, which is easier to use but has less functionality, or a text editor with code, which is basically the opposite. It's more difficult to use but greater functionality. From a programming perspective, the Industry 4 change is towards autonomous programming. So using auxiliary systems to gather information that will allow the robot to alter its task. All 3 of these still have their uses. I'm not saying that one has superseded the other. So there's no one-size-fits-all approach. For example, if getting started with robotics and not needing extreme complexity, an online robot is great. It's simple to program when compared to an offline robot. However, if more complexity is required, offline programming may be the way to go, and from there, autonomous programming. Can you move to the next slide, please, Sam? So I'm now going to talk about the challenges. Of course, applying Industry 4 ideas to automation isn't just limited to robots. Many systems can be automated, at least partially, using sensors, as both John and Richard have already said. The level of automation required dictates the challenges, as you'd expect. So irrespective of the level of automation, the first challenge is always what to record. As noted earlier in the presentation, big data is one of the 9 pillars of Industry 4. There is so much data available, and therefore the challenge is what data should be chosen to be recorded. What processes in your system will benefit the greatest from automation? The next step is how to collect the information that has been identified. So which sensor should you actually use? The most obvious option is not always the best, right? So as an example, think of fluid running through a pipe. When fluid is identified in a specific area in the pipe, a shut-off valve should be activated. One option would be obviously to use a vision system. And at first that might be great. You'd think it could identify the liquid, no problem. However, what if in the future the liquid changes color, or indeed the pipe changes color? Therefore, a better idea might be to use a capacitive sensor. As I say, the most obvious option is not always the best. At this stage, as we say though, Industry 4 changes to a process can already be made. The data that can be used to improve processes, get diagnostics on the equipment, and make incremental process changes, just as John was saying with the bandsaws in NMIS just now. However, if real-time process change is required, real-time validation of the data as it's collected is the next challenge. And this can be broken into kind of 2 stages. Firstly, what level of validation is required? This is decided based on what data is being used for. So what are the potential risks of an accident, for example? Or should a second form of sensing be used to help with verification? It could be that you can compare your data to a calibrated source, for example, a CAD model, or in the case of the fluid flow example, maybe just regular calibration of the capacitive sensor is satisfactory. The second stage of the real-time validation is the actual complexity. So if the validation is complex, maybe there's lots of information that has to be transferred, computation power becomes very important, as does well-written programming, to make sure it can keep up with the process as it's working in real time. The final stage is how to translate this verified information into real-time outputs. So depending on the requirements, this may be a task for machine learning. However, if it's more constrained, a simple rule-based algorithm written by humans might well be sufficient. A perfect example of the challenges facing automation integration with Industry 4 is the driverless car industry. We all know the challenges that we've seen in the media of driverless cars, and a large part of the reason for this is linked to these 4 challenges here. However, as I say, in order to transition towards them in relation to automation, not all of these steps have to be followed. As Richard and John have both spoken about, retrofitting sensors to current equipment and intermittently analyzing the data and altering the inputs is a step that has a high likelihood of benefiting a company. Can you move on to the next slide, please? This leads us on to the opportunities and benefits of integrating Industry 4 with automation. As said, linking sensors onto current equipment allows data to be gathered that was before lost. This can lead to unforeseen process improvements that may not be immediately intuitive, which in turn can increase profits. If going down the route of real-time alteration to processes and a higher level of autonomy, Industry 4 can lead to improved productivity, as the ability to alter process inputs in real time means that equipment will have less downtime. It's obvious, right? This is linked to, from there, increased flexibility, as a larger product range is able to be worked on. You might have, before you didn't have the time to look at certain products, now you do. In terms of impact of robots, this is really significant, because robots are best suited to processes that are very repetitive but cannot handle versatility. So if we have the ability to be able to increase this versatility of a robot, therefore, potentially we can open many doors. We're still obviously at early days of that, but as time progresses in technology, this versatility of robots is definitely going to be seen. Another benefit of real-time alteration to robot paths is the increased process responsiveness. Unexpected inputs to a process are just now a common issue with robotic systems. For example, if a part is not where it's expected to be during a pick and place operation, the robot won't be able to keep going. Therefore, the ability to be able to be responsive to unexpected process changes would help to reduce this issue. The final benefit is probably the most obvious, the fact that investment opportunities can increase. This can come in a range of ways, from changes to machinery operating parameters that give greater productivity, as mentioned, to the possibility to bid on new contracts because of increased process flexibility. Next slide, please. I'm now going to go on to describe a couple of projects that the automation team within NMIS are currently working on. The first is based on challenges already mentioned, specifically those of the verifying and translating the data. So the idea that we have is to use a vision system to scan the part and produce a 3D point cloud. From here, the idea is to use the point cloud to create toolpaths. So the first step is to verify the data that is in the point cloud. We'll design test parts, get them manufactured with a variety of design features to try and cover a large scope of different eventualities. We'll then scan these and produce a point cloud. To verify the point cloud, we'll compare it to 3D CAD model data we have, because we designed the parts, so we have the CAD model data available. Once we've verified the point cloud, we can then move to the translation step. And that's the more tricky step, which is actually using the point cloud to automatically design the toolpath, especially in real time. But once we're confident the system works, the aim is that we'll be able to, 1, create completely new toolpaths, 2, alter toolpaths to deal with unexpected disparities, as I mentioned, Or 3, update a toolpath to work on a similar but unique part. So maybe, for example, it's a spraying robot, but you can feed in different sized or different shaped things it needs to spray. So maybe different sized liquid containers. Next slide, please. The second case study is our Auto Forge. So the aim here is to make a closed loop system of inputs and outputs in the hot forging cell. The idea is, just now, the cell, it picks up a billet, it places it in a hot forge, removes it from the forge, places it in a press, removes it from the press, and then places it on a rack. Currently, it works by using positions taken from historic data. So, it knows, it's meant to know exactly where the rack of billets is, exactly where the forge is, where the press is, and where the rack is. But therefore, any change in position means that the system malfunctions, as we spoke about. So this project has 2 stages. Firstly, we're going to place sensors at various points on the system to record information such as position and temperature. Therefore, if the billet does move during the process, for example, when it's in the forge itself, when it's getting heated, the part can still be identified and work can continue. It can be picked up and moved on to the next stage. The second stage of this work is to feed in and improve the consistency of it. So maybe, for example, if we have the materials information, if the billet temperature changes, the force and the pressure ramp rate of the press can be altered to give a consistent output to the actual component. These are just two projects that NMIS are currently working on, but of course, as we said already, there's many ways that automation can be increased using Industrie 4 just with simple sensors. As noted, the challenges are based around what to record and how to record it, and then depending on the level of automation sought, how to quickly verify an action as data. But even fairly simple diagnostic data from current systems can make a significant difference, especially to older equipment. It still performs absolutely fine, so there's absolutely no reason why, as a company, you would want to strip out equipment which still works as required. A theoretical example of this is a steam engine, and I'm now going to hand over to my colleague Jafar, who is going to speak about just such a project. So Jafar, over to you.
You're muted, Jafar.
Sorry, rookie error there. Thank you, Thomas. And thank you everyone for joining the webinar. So this is a live project that I'm currently leading, and it's entitled Industry 1.0 to 4.0. So just a little bit of background with the title. So Industry 1.0 there is in reference to the first time when we moved from manual labor to using steam as a source of energy, to drive equipment. And obviously, after Industry 1.0, we went on to using electricity, and thereon, deploying computers on the shop floor, to where we are now in Industry 4.0 is how do we connect all these individual systems so they're talking to each other, allowing for a more productive and efficient manufacturing environments. So the steam engine here, as you can see, we're working with, was donated to us by Summerlee Museum, who are based in Cottbridge. And a little bit of background on the steam engine. It was used in Airdrie Cotton Works in Goldie's mill. And as you can see here, there's a man with a steam engine. We can't identify who this man is, if he was the manufacturer of the steam engine, but this is the best picture that we have, showcasing where it was used. So some of the challenges as well that the museum has is how can they display some of the items that are stored in their warehouses that are just collecting dust. So this project will kind of show how we can do that. And it's also an opportunity for us to showcase some of the Industry 4.0 technologies. That way we can invite members into the center if COVID wasn't around, obviously, and show them how they can apply some of these technologies. And it's also another way for us to engage with STEM activities. And also, whatever I show you in this slides, it's not limited to one sector. You can apply these technologies in other sectors, including manufacturing also. So yeah, I'll also speak about how some of the pillars that Richard touched on, how those are applied in this project. So if we can move on to the next slide, please. So one of the pillars that we deployed here is the simulation. And as you can see here, what you're looking at just now is a scanned model of the steam engine. And how we achieved this was using a standard DSLR camera. We deployed markers and scale bars onto the steam engine, took multiple pictures from different angles, and those were stitched together to generate this 3D model that you're seeing in front of you. And the model contains high quality texture applied from the original photographs. And for accurate dynamic analysis, model was deployed in reverse engineering software, creating a solid body assembly. And what we can do with this model is that deploy it in a VR environment where we can get data from sensors into the digital model to drive the steam engine. So if we can go on to the next slide. So this is the CAD model that we were able to also generate from those scans. And what this lets us do is that for any missing parts or defective parts, you can reverse engineer those, by simply scanning. So once you have your scan, you've identified what your missing parts or the defective parts are, you can manufacture those, or depending on whatever processes are available to you. So that's the simulation pillar that was deployed. And then if we can move to the next slide. And one of the other pillars as well is IIoT and ERP integration. So what you see in front of you here is a device called BitsBlock that was manufactured by one of our members who are called BitsList. And what we're doing there is that we will be deploying these 3 sensors onto the steam engine. So that way we can monitor the revolutions per minute as the flywheel is rotating. From that, we'll be able to calculate the amount of energy the steam engine generates, and we'll be obviously feeding that data into a digital model to animate that model. We'll also be deploying a current transformer just to monitor the machine status, if it's on, off, or idle, and the power generated again, and a MEMS microphone. And what this will do is that it will just measure the ambient noise level. So if it's a noisy environment, we can send alarms, to the guys on the shop floor just to let them know to put their PPE on. And the BitsBlock device, what it does also is that it gets data from the ERP system that we're using, and it can advise the shop floor technicians as to what job they need to be working on next. Of course, we won't be using that feature for the steam engine, but that capability is built into this device. So if we can move on to the next slide. Another pillar that will be deploying in this project is the visualization. Unfortunately, these 2 images, they're not really images, they were supposed to be GIFs to show you what the animation looks like. But on your left-hand side, there would have been an animated cross-section of the steam engine. So this was more for engaging with the STEM activities. It's just to give students a kind of idea of what a steam engine looks, from the inside. But unfortunately, we're not able to see that just now. And then on your right-hand side, there's an animated model that was developed in Unity. And what this allows us to do in a mixed reality environment or a virtual environment is to interact with the model. Users will be able to play, start the steam engine animation, stop it, control the speed, and we're also looking at gesture control. So that way it's a lot more interactive, where users can, for example, wave their hands. The faster they wave their hands, the faster the steam engine would rotate. So yeah, so as I mentioned earlier, data will be going from the sensors to drive the digital model. It's another way to display a steam engine, any information related to the steam engine in a virtual environment. So that was one of the challenges that the museum had, due to the diverse, range of audience that walks into the museum. You may have from kids all the way to experts that might have worked on these bit of equipment. How do you get that information across? Augmented reality, once again, it's just a different approach for the museums to display their items that may not be may not have space, in the museum to display. So this is just another method for them to consider. And then obviously we have mixed reality. So in this case, we will be using a HoloLens. It just kind of gives another layer of interaction with a digital model. If we can move to the next slide. So yeah, this is just the final slide, giving you guys an overview of the project. So obviously you can see the sensors, that data going into the bits block device, and then from there onto the cloud. Just kind of a bit of information there. You don't need to use cloud. You can use your on-premise storage solutions. And then from there on, it will be that data will be getting deployed into multiple solutions, VR, AR, XR, and ERP included. And also you can deploy it in any dashboards, open source dashboards. And then at the top right hand side, just to give you an idea of some of the softwares that we used to develop the solution. And then at the middle of the slide, an idea of just how much the solution cost in total, especially the hardware. As you can see, the sensors are really low cost. So it just gives you an idea if you're thinking about a project like this in your manufacturing environments, how low cost it is. We have graduates and students leaving school. These are the types of skills that they're picking up in schools, using Raspberry Pis and Arduinos. So if you do have any students in your facilities, make sure you're getting them to work in projects like this. So that will be the end of my presentation. And if you guys have any questions, please do pop them in the Q&A section. Thank you.
Thank you, Richard, John, Thomas, and Jafar for your illumination, erudition, and contributions there. Very interesting. I believe that we've garnered some questions from the audience during our speaking session there, and I wonder, John, perhaps if I could ask you to address the first.
Yes, I personally got a question from Paulius Stulger. Hope I said that right. The question was, how far into the resume development are you? Particularly interested in how you'll be connecting the machines with different communication protocols onto one digital platform. So currently the resume development is, we are going out to tender at the moment for the storage solution, or the storage work pack, and the data analytics work pack, but we are still having conversations about the networking, industrial IoT, and enterprise. So yeah, we're happy to talk to anyone about these kind of work packages if you're interested. At the moment, for the industrial IoT, which is kind of relating to the end question of how we're going to connect all these different machines with different protocols, we've been speaking to companies like Siemens, Highby, Novatech about their sort of edge devices, local edge devices, which will allow us to communicate between the machines and get that data from the PLCs, CNCs, or sensors themselves, and get that over the network and into the data lake themselves. This is going to be one of our major challenges, is connecting all these machines, because as I said in the presentation, we do have a very vendor diverse machines, so it's not all necessarily that all these machines have one particular protocol. So yeah, it is a big challenge, and it will be the challenge of resume. I hope that kind of answered it.
Thank you very much, John. Thank you very much. I've also received a question here, which was just off the back of your contribution there, Jafar. It relates to the low-cost generation of data from machines. So you'd highlighted the data that you generated from the steam engines there. The question is, can NMIS support SMEs and micro SMEs generate similar data from machines that they have currently deployed?
Yeah, absolutely. And I think what John spoke about with the resume testbed and what we're trying to do, it will just highlight the different ways of acquiring that data from machines, whether that's machines that have a form of connectivity, or if it's legacy equipment similar to the steam engine. There are ways of getting data from your machines. Yeah.
Thank you very much, Jafar. Another question which I'd like to direct to yourself and then perhaps open up to the other panelists. We've received a question around the visualization softwares which we use to convert digital masters, so converting them, so CADs to 3D and AR and VR. I was just wondering if perhaps you could talk quite quickly about some of the software solutions that you'd listed.
Yep. So once I think the model was scanned, 3ds Max was used to kind of develop that 3D model, and some of the animation work was done in Unity, as well as SolidWorks, I believe. And yeah, so in Unity also you can, it's a free kind of platform that you can download and play around with. Especially with animation and deploying various types of information. So if you have, any information for your workforce relating to, standard work documentation, and there's a certain method, you can deploy that through Unity and, onto devices such as iPads and tablets. So those are the kind of key bits of softwares that we used. If you'd like any more information, we do have people within the digital team or the metrology team who are experts at using those software. So if you'd like to find out more, then just drop me an email and I can forward your inquiry to the right person.
Thank you kindly, Jafar. And I suppose we'll just open that question up to the other panelists just quickly, whether you concur with Jafar or whether you have anything to addition there in terms of the softwares deployed.
From our perspective of resume, we are going to be very open and agnostic. We want to be able to run all software on this resume testbed. We don't really want to be kind of pigeonholed into, say, one kind of manufacturer. I don't know, Siemens, Beckhoffs, etc. So the idea of resume is to be able to run any software, so you can test out in any of your kind of software you want on this kind of resume Industrie 4.0 testbed.
Thank you very much, John. And one final question here that I've just received, and it relates to you directly, Thomas. The question states you'd identified a range of measures on the steps to realizing automation for a business. Can NMIS help organizations decide which is the most applicable, apt for them?
Yeah, of course. That's one of the services we offer. Usually we'll have meetings and back and forth, and we have to work out. Firstly, usually how we'll do it is we'll look at what the process that the company does, and then from there, look at kind of sub processes and which ones are maybe more viable for automation and which ones are less viable. So if there's something extremely repetitive, for example, and it takes up quite a lot of time currently for a human to do, that'll be a very good example of automation. But if it's something which is quite quick for a human to do, but maybe requires, I don't know, for example, like looking at leak rate, maybe like occasional drops of oil out of a system in a dark area, that's something which a human can check very quickly, and then compare that to return of investment as well. And by looking at those two factors combined, so both the return of investment and the applicability of automation to the process, then kind of go forward from there, and start drawing out, as we spoke about, these 4 challenges. So what data to collect and how to collect it.
Thank you very much, Thomas. And in respect of time, I think we're going to close the Q&A session at the moment, but we very much invite questions from yourselves, ladies and gentlemen. We have provided speakers' contact details in the chat box, and also if we could just see here the email address NMIS inquiries. We do welcome any kind of inquiry. Thus, if any element of today's presentation has been of interest, then please do connect with us. There are a range of support mechanisms available at NMIS, a wealth of experience and expertise. So whether it's the provision of advice or inquiries around joint research projects or direct support, then please do connect with us. So all that remains for me to do this morning is to thank our speakers respectively. So thank you, Richard, John, Thomas and Jafar. To thank the marketing team for organising the event this morning. Thank you kindly, Debbie and Laura, once again. And to thank yourselves, ladies and gentlemen, for your continued participation and attendance. We look forward to seeing you at the next series in the NMIS Insights webinars. Thank you kindly.
Thank you, Sam, and thank you to all our speakers today. And just a reminder that a survey will be issued shortly. We'd be most grateful if you could complete that. It will just take 2 minutes of your time. And a recording of today's webinar will be available tomorrow on our NMIS YouTube channel. So feel free to have a look at that or share that with anyone. And that's all for today. So we hope to see you again soon. We have another webinar coming up on the 18th of November on Future Forge. So if that is of interest to you, have a look on our website and you can find out some more information about signing up. Thank you very much, everyone.
Thank you.
Thank you.
Thanks, everyone.
Thanks very much, everybody. Cheers.